break, we discussed the motivation of this paper, right? And the key idea is how does climate change affect the rate of inflation, and thereby how does it affect our central banks' responses? I didn't give you a chance to ask questions before the break, so are there any questions on the motivation, on the big setup, on the big picture so far?
Can I just have quick questions? So for this model, right, our baseline is the laser fare, and that laser fare, is it just the IAM plus the sticky price?
Yes, that's right. And we will see, but that's exactly right. So the laissez-faire is we take the IIM and the Keynesian model with sticky prices, and then but laissez-faire means we are going to project the next 75 years. And in those 75 years, if we do not mitigate, something will happen to emissions, right? Something will happen to temperature, something will happen to GDP, something will happen to inflation. So it's not the laissez-faire doesn't mean the world how it looks like today will tomorrow will look like today, the day after tomorrow will look like today. So the projection until 2021, until 2100, it's not like that their laissez-faire doesn't mean that we're looking like the world looking like constant. Inflation will be always 2%, and output will be always kind of at its growth path, and no, that's not what laissez-faire is going to mean. It's like we don't mitigate today, and then the model has predictions of how the world economy is going to evolve. What's going to happen with consumption? What's going to happen with GDP? What's going to happen with emissions? What's going to, right? All these things will evolve endogenously in the laissez-faire economy if no mitigation policies are taking place. And then we will be looking at what happens to inflation. How important is the climate-inflation force in that environment? So you can think about the laissez-faire. In the laissez-faire, only the climate inflation will be effective. There will be no greenflation in the laissez-faire. But then in the mitigation scenario, we will have the laissez-faire plus the greenflation. That's exactly what we're doing.
Another quick one. So like when we bring the data into the model for projections, right?
Yeah.
Just from a perspective, if we present it to someone, do you think they would be more convinced if we do all our parameters by estimation or by calibrations?
By estimation.
By estimation.
It's much more convincing, absolutely. You have informed the model the best way with the data, and if you can, go always for estimation. Go if it's possible, go for it. Now it's going to be challenging.
Yeah, because actually, we actually try to estimate just a small part of that before, just even for the
with Michael Binder, yeah.
For the sorry, I forgot. Can you switch back to the slide with the calibrations?
This one?
Yeah, that one. Yeah, so even with the elasticity of intertemporal substitution, right? Actually, we did try to estimate that before, and even for that, there's one separate paper just for that.
Yeah, that's right.
So it just means if we actually attempt to do everything, it would be a lot.
It would be a lot, and frankly, sometimes you will not be able to estimate all parameters. There's what's called identification issues, in a sense that some parameters cannot be identified. Like for instance, if you go to the Phillips curve, there is a little bit of let's go back here, right? If you think about the Phillips curve here, right? Suppose you would estimate this equation, say with OLS, the data would only tell you the one coefficient in front of marginal cost, right? Suppose you have data on marginal cost, data on inflation, and you estimate this equation, then you will be able to estimate beta. But here, you will only be able to estimate this ratio coefficient, right? I mean, the data will give you this should be 0.1. But we know in this model, this 0.1 coefficient consists of two parameters. You will never be able to identify both parameters together, right? Because there's an infinite amount of combinations of theta and omega that gives you 0.1. So that's why some of the parameters will not be identified. So to be more precise, what they are doing, they're not estimating all the parameters. They're estimating those parameters that are identifiable. So that's basically what we do. But nevertheless, if you can, even estimating a subset of parameters is preferable to parameterization. But be advised that is an important element. I mean, this here, estimating the model, I talked to Gauthier about it. You know, just estimating the model takes more than 1 day of time. So you hit a button, on your workstation, then you go, and after 24 hours, if you're lucky, you will have estimation results. This takes a lot of time to estimate because there's a lot of computations. In other models, it's quicker. I mean, I have estimated models that you can estimate in 10 seconds. Okay, so it really depends on the method. Okay, other questions? So then, there is what the authors call a methodological breakthrough. Okay? What do they have in mind here? Well, in their analysis is that the standard view, this is what we did yesterday and today in terms of the New Keynesian model, the standard one, is that once you have a shock, the economy adjusts but comes back to the steady state. That's what they call stable propagation mechanism, right? So going back to our previous slide decks, right, when we're looking at impulse responses like those, right, you have a one-time shock, and then the economy, after adjusting, comes back to the steady state. That's what they call the standard view, where you have these fluctuations and they are decaying over time. With that climate model, there's a big problem there, because we're going to have what they call permanent effects. So in other words, emissions are accumulating over time, and they're going to lead to a permanent change. So temporary shocks are going to have permanent effects. One idea is, if we don't mitigate today, we will be permanently changing how the economy is going to look going forward. That is methodologically complicated. It requires a different way of thinking how to solve the model. And so there is essentially no steady state after shocks. Go ahead, please.
Sorry, like previously, like when you simulate like 10,000 kind of oscillation.
Yeah.
Like we can see that it's fluctuate, but it's kind of like oscillate around a constant
mean.
Like,
That's right. But not here.
Here is like the path is completely different.
That's right. So it could be that in terms of say, suppose you do laissez-faire, you would see emissions going to do like this. That's the idea. Okay. So there are going to be trends that are non-trivial, and they're going to depend on policy, for instance. Okay. And the reason why that climate problem produces that is, among other things, is that this model is a model of degrowth. Have you heard about that? Degrowth basically means that this carbon accumulation, right? So in this economy, what's going to happen when there are emissions? There's carbon accumulating. And that carbon accumulation is decaying incredibly slowly. So we are basically always accumulating more carbon. And that, the way this model is connecting this is that productivity is going to be negatively affected from carbon accumulation. So for instance, if carbon in this economy goes up because of emissions, so if carbon goes up, then productivity goes down. Permanently. So meaning, right, if you have more recurrent droughts, more recurrent floodings, well, productivity in the agricultural sector, for instance, is going to be lower. For a given amount of seeds that you put in the ground, with climate change, more carbon, there's a larger portion of those seeds getting destroyed by water storms, windstorms, drought, heat waves, and so forth. So the productivity that is measured every hour that you're putting into the production of agricultural goods is going to have lower output, basically. So intuitively, and I'm using maybe some very simple notation for that. So think about a production function y that is going to be a function phi, we have that down there, phi of m times L. Okay, think about that production function, right? So you're producing with labor input that produces output as before. But now think about, you abbreviate carbon with the letter M. I mean, at some point we cannot use C because C is consumption in our models, right? So this is carbon. Okay? So carbon is affecting the productivity of labor. And it does that in a negative way. So you may just have a minus sign underneath to remind yourself that if M goes up, this expression here goes down. Carrying the idea that when there's carbon, when there's climate change of more carbon in the atmosphere, it's going to lead to a reduction in the productivity of any labor. And the way this model works is that these climate damages, and these climate damages are don't scale proportionally. It's not proportional like in the solid growth model, that everything scales proportionally. This thing is not proportional with technology. And that gives rise to this problem that you don't have a well-defined steady state. You don't converge to a steady state where output and labor productivity move by the same proportion. So in the Solomon model, right? I mean, maybe let's write this down. In the Solomon model, right? How do we do this typically in the Solomon model? So let's write down the Solomon model. Okay? So suppose in the Solomon model we have a production function that looks like yt is equal to zt times lt to the alpha and then capital to the 1 minus alpha. Okay? So that's a typical production function in Solo, right? And suppose zt grows over a long period of time, right? So suppose zt has a trend that goes up like this. Well, then how do we solve this Solo model often? Well, alpha is between y and 1. You're rescaling the model, right? You divide this by zt over lt. Right? So what we're going to do then with Solo is we're going to write that yt divided by zt times lt is equal to kt over zt lt to the alpha, 1 minus alpha, right? That's what we typically get, right? So you divide the entire equation by zt over lt. And then what you show is that, with this scaling, now output grows at the same speed that the denominator grows, right? Technology grows over time, so this is output per capita growing at the speed of z. So in other words, this thing grows at the same speed as this thing, so there's a steady state, but this ratio is constant. So that's what and we typically call that in a new variable, often this is called like yt tilde or so. And so yt tilde has a steady state, right? If there's no shocks to z, then this thing eventually is going to be flat, it's going to be constant, right? Because output, the level of output grows at the same speed of z, and then also capital grows at the same speed of z. So that's what we typically have in Solo. In this macroclimate model, not there. Because, we don't just have a zt sitting in front here, that carbons affect that z. So the more carbon we have, the lower it's going to be productivity. So whether we are in laissez-faire or in mitigation, this object is going to look different. And then that prevents us from having a steady state for, say, y. That's the basic idea. All right, so how do they deal with this? Well, they are showing that you can use nonlinear methods. You can use nonlinear solution methods to solve this model that do not require solving this model like we did it before. So one idea is that, right, when we were solving the model, we always needed a local steady state. Like for instance, when we did the local solutions, we did log linearize the model, right? We had something like yt head is equal to the natural logarithm of yt divided by y bar, right? That's how we define when we log linearize the model, how we transform every variable. We log linearize the model by taking the logarithm of output and divide that by the steady state. And we did the same for inflation and for consumption. Okay, so log linearizing means, and Min asked that question on Monday, but you need to know that steady state. And it needs to be a constant steady state, otherwise this definition doesn't make any sense. With macro climate, this thing is not going to be constant, and it's not going to be on the balance growth path. So we cannot log linearize. That's the basic problem. So with macro climate, the way the authors think about this, it's impossible to log linearize and use local solution techniques. You will need to use global solution techniques to solve the problem. In other words, you're going to solve the non-linear model. You skip that linearization step. And they are working in Dynare, so we will be playing with code in Dynare, where I will show you how you can solve that model non-linearly. You don't need to log linearize. So we will definitely do this week, possibly tomorrow. Let's see how much progress we can make, and at some point I'm going to say, okay, let's call it. We're not going to go further on the slides, but let's then use MATLAB. By the way, how are you guys standing on getting MATLAB and Dynare on your computers? Does everybody have MATLAB and Dynare on your computers? Really? Fantastic. So bring your laptops. So tomorrow is Thursday. Yeah, bring your laptops tomorrow. We may, in the second half of tomorrow, start playing with MATLAB. For sure on Friday. For sure. Okay. Good. So that's basically the bottom line there. And this is maybe because this is a flip slide. Those two are now the same bullets on the next slide. And so these are the same. And now they explain how they are solving nonlinearly. And that's how you have to think about that. So this is the explanation for how to solve nonlinearly. Okay? Solving and estimating nonlinearly. And it goes back to a famous paper published in Econometrica 40 years ago. So that's the same Taylor than with the Taylor rule. So this is John Taylor and then Ray Fair. They published a paper in 1983, and that actually allows to solve the model with non-linearly with a transition path where the initial state is different than the terminal state, where you can have permanent changes. And the beauty is, this is all implemented in Dynare. So there is a hidden gem here. You can use that inside Dynare. So part of our course is introducing you to Dynare. When you go and you do the standard Dynare usage, you're going to use the guess and verify local solution, the stock simul command that you've been working with inside Dynare, and we will review that tomorrow or on Friday. But then there is a hidden gem inside Dynare that, without using log linearization and local solution techniques with a steady state, you can use this Fair-Taylor solver that solves a complete nonlinear model and gives you the solution for that. How beautiful is that? And it's just a different command you're using. You don't need to do extra coding on it. It's just using a different command and say, I want to use this solver, and then you can solve the nonlinear model with permanent changes. So I'll show you how that's going to work inside that. Okay. Perfect. Now then, they don't stop here, and that's not yet in Dynare, that's their own code. Then they also estimate the model parameters. So they use this solution technique to then, code an estimation, and we're not going to do that here. This is too much for our purposes, more like PhD level, frankly speaking, not in terms of level, but in terms of we would need to review how do you estimate models in the first place, and so that's going to be more challenging. Okay, but we will be doing certainly the studies of the solution and the transition dynamics. Okay. Any questions on this? So this paper, and when you're writing a new paper, even when you write your master thesis, any research, you need to make sure as an author to embed your research into the existing literature. It's very important to locate, to tell the reader this is the contribution of my work to the literature. And like when you are submitting papers to journals, it's essential to document, okay, there is the literature, and there's a gap in the literature. And I fill that gap with my work. My work finding this, fills that gap. Other ways are saying, there is this literature here, and there's this other literature there, and I combine those two literatures. So always make sure to inform the reader what is your contribution. Otherwise, it will be very hard for people to assess what you're trying to do and what you are contributing. Okay? And then this paper basically contributes to, if you like, 3 strands of literature. First is it contributes to this more integrated assessment literature, thinking on the long run. And I'm thinking about the long-term effects of carbon accumulation, going back to Nordhaus and others. But what these papers ignore typically are fluctuations around these long-run projections. And more importantly, they ignore the price and inflation dimension of this. There's nothing on inflation, nothing on prices, and nothing on monetary policy and other related elements. So then we have climate models that focus on the short run, and those are what's called EDSG, where E stands for environmental. It's the environmental DSGE models. Okay? So they have elements of carbon accumulations and nominal rigidities, and it's by now a really emerging literature, but they don't have these long-term trends in it. So they do some really interesting work based on short-term fluctuations, but they don't have these long-term trends. That's the, so to say, drawback there. They don't have that. And so you can think about that this paper combines those two in the first place. And then of course, it folds this into a really standard Keynesian model. I mean, as standard as you can think. And you will immediately, when you're going to start reviewing the equations now, immediately see how this paper fits into what we did in this class so far. Any questions? It's like all great papers to take a look at if you like, and others, and you kind of catch fire on this type of work. But then let me maybe give you an outline for what we're going to do next. Okay? So we finished the intro, and we're going to now talk about the new Keynesian climate model. I'm going to give you the intuition what the estimation does, and also what the estimation results are. Okay? And then we're going to spend lots of our time thinking about the laissez-faire versus the mitigation. What are the key takeaways? What are the key results of this paper? So this is where all the results are. And then we're going to take this model and say, now we're going to take this model that we've estimated, and now we're going to think about, okay, let's do a policy experiment. What happens if monetary policy is structured differently next going forward? What, if policy either explicitly or not explicitly, thinks about the climate change inflation effects? And what are then the changes to do? That's basically what we're trying to do. All right, so let's start about the model, and let's maybe first have like a verbal discussion of the model. There are 3 entities operating in this economy. There's households, there's firms, and there's a central bank. That should sound very familiar to folks. Households are essentially very similar to what we've done so far on Monday and yesterday. So they choose a consumption, they choose savings, they choose how much labor to supply. So very standard, if you like. And they are maximizing the temporal utility. What's new relative to what we did is there are demographics in this model. So there is a time-varying population. So population is going to have a trend in that model. And in fact, population is going to grow in this model. So what we're going to see is that population is going to, change over time, and there's going to be more people living on our planet. Second, firms, they are doing also something very similar to what we did in class yesterday and today and on Monday. they are choosing labor to maximize profits, and they're choosing price. And here comes the first tight connection on the slide deck that we covered yesterday on a Monday. They're using the same Rothenberg adjustment cost for that. It's symmetric though, right? And they have a slightly different argument in their adjustment cost function, but it's the Rothenberg price. So that is now paying off that we are experts on what Rothenberg pricing means. That we can just hop over this very quickly. And then they have a Taylor rule that's similar in spirit to the Taylor rule we've considered. It's a little more complicated, but it's not like the end of the world. Now let's put a little more structure on some of the new things in words that this model has. Okay? So there's like 5 little details that they have changed relative to the standard model, and they do that in order to be able to estimate the model. Okay? And here's how this works. Okay? So the consumption savings is standard, but the population size, that's maybe the first element that's new. So what they're assuming is that the population today is a function of the population yesterday and the terminal amount of population that we're going to have at some point. And L is the speed parameter by which we're going from some initial level of population to the terminal level of population. So let me graph that to you. Okay? So there's a way to graph this. So suppose you're drawing on the x-axis time. So suppose you're drawing time on the x-axis. And let's suppose you have some initial time, t minus 1 here on the initial, and there's a level of population, say that's 8 billion people. So right now we have on our planet 8 billion people. So this is the population, this is plotting LT. And we have 8 billion people living on our planet. So that's where we are right now. So if we stick in 8 billion people here, and we assume some parameter for L, then we need one more thing, namely LT. What is LT? LT is the terminal amount of population. And the authors make an assumption, I believe it's 12 billion people. So they say, could also be 10, I have to recap that. They're saying, population is going to asymptote eventually from 8 billion people to 10 billion people. 12. That's the dynamics. So population is going to increase over time, right? As time progresses, population is going to increase, and it's going to level out at that level. So the broken line is L capital T. It's going to be L capital T. By the way, this is really bad notation. I mean, this is an L, and that is an L as well. It's really bad notation. No? So this is a parameter, while this is of course this. So I need to be very careful, right? So this is actually, this must be a different, letter type. So we have L capital T is equal to 12. Okay, that's the idea. Okay, so the terminal L is 12 billion people by assumption, and initial L is going to be 8 billion people, and then this curly L determines the speed by which we're going from 8 to 12. So for instance, if L is equal to 1, right? If this curly L is equal to 1, this thing disappears, then we're going to 12 billion people. That's how we have to read this. If this L is close to 0, then it takes a long time until we are at 12 billion people. So this is like a geometric parameterization on the speed by which this thing goes up. So in other words, we could also have a different color in here, like greenish, where the population could maybe also go much quicker up there, depending on the value for the curly L. And I realize also this here needs to have a different notation. So this is LT. So L prime is bigger than L. So the idea is that if you have some L, some speed parameter for is, if you increase that speed parameter, if you make that speed parameter L prime bigger than your original speed parameter, then you're going to go quicker to your terminal population. That's the key. All right. Good, good, good. Any questions to this? Next is, they are also refining a little bit the, in this model how agents or households are. There is actually heterogeneity in households. The households are not alike. In particular, what they assume is that households can be of low productivity or high productivity. And when households are low productivity, low productivity, they become unemployed. So in other words, in this model, we have two types of household members. There are, pardon me, but there are the unemployed and there are the employed. Okay, that's how you have to think about it. There's two types of workers: unemployed workers and employed workers living in one family. The unemployed people get unemployment benefits from the government, and the employed people make income.
Sorry, is it similar to those like retired and non-retired also?
Yes, that's well. You're all living in one household, but it basically breaks recorded equivalence. That's right. So this assumption, there's income risk in the sense of you may have the labor income or not, right? So if you're employed, you have labor income. If you're unemployed, you don't have any labor income. In that sense, it's risky because your type changes. You may be unemployed today, but tomorrow you may find work and you join the pool of the employed and you have more labor income. You guys, some of you may fall unemployed in the next period and join the pool of the unemployed. So there is risk in every period whether you have a job or not. And so that goes back to McCabe. And of course that means that you are thinking about recurring equivalence in a different way. Because if some of us are unemployed, then that has implications. Okay, so long story short, and we will see the details of it, there is income risk in this economy in terms of for the household side. So why do they put this in? Well, this thing gives rise to the so-called discounted Euler equation. So we're going to see a change to the Euler equation. There is discount here. What does this do? Well, the reason why they have this is because they want to do these long-term forecasts. So if we go back to slide number 4, right, one key element in their analysis is this: they want to do forecasts for 75 years. They want to do these very long-term forecasts. The problem is that in this economy, if they have no income risk in households, these households can perfectly forecast where the economy is going to go. And what the problem with that is that it is delivering an ugly result, namely that there is going to be, when you are today and you know perfectly about the future in the next 75 years, because of the Euler equation, you're going to roll forward a lot of your action to today, when you see the economy is going to go into recession in 40 years from now. So long story short, the reason why they want to break that tight link about I change my consumption today as a function of the long-term real interest rate, of the long-term development of the economy. When I see the economy going down the drain in the future, I'm going to react immediately today with my consumption by a lot. And to break that very tight link, they are putting in this discounting, the labor income risk. Because now you don't really know whether you're going to be employed or unemployed in the future. You're going to do precautionary savings. And you are going to, slow down your responses. Essentially, what we're going to see when we look at the equations, and I'm going to point you to that equation, it's going to mute the effects of future expectations about the economy. So that discounting here, that discounting is going to, you're going to see it's going to be one parameter that's going to mute expected future, consumption, expected future inflation in the household decision. That's what this does. It puts a discount on that, like it reduces the quantitative importance. And we'll see, today equation that, how that actually shows up. All right. On the first firms maximize profits subject to this Rothenberg price setting rule. And then there is one extra element, namely that technology is growing, but the speed by which technology is growing is diminishing over time. That's what this does. So let's maybe also graph this, and here the notation is much easier. The way how we want to think about, say, the time profile for ZTs, let's draw the time profile for ZT. So this is again time T, and here I'm drawing ZT. ZT is growing over time, but at some point it's going to attain also a constant level. So technology at some point is going to stop growing. This is 2025 or 2026. This is 2026, and this is 2100. And it may take decades, but technology growth is slowing down over time. That's basically the idea. Why are they doing it? Again, because they look at GDP in the data, and they say, look, at the world level, it seems like that the growth rate of GDP is declining in the data, and the past, and that they assume it's going to continue doing it. So the way how to do this is, right? This is the level of ZT. Right? This is the level of ZT growing over time. It's a function of the level of ZT yesterday, right? So my technology today is technology yesterday, plus 1 plus this growth factor. So this is actually the growth rate of Z, and they assume that that growth rate is going to decline over time. So that growth rate is following itself, that this autoregressive structure, well, delta Z is a parameter that is larger than 0. So delta Z is larger than 0. So what does this mean? Well, you see that over time, right, if this is like 0.5, if suppose delta Z is 0.5, then that means, whatever GZ is yesterday, you multiply that by 0.5, so you only have half the amount of G left today relative to yesterday. Right? So you can, if you graph this one, so let's graph GZ over time. Right? Graph GZ over time. This is GZ, comma T. It's going to have this path, right? And eventually it's going to approach 0. So GZ over time is going to decay geometrically to 0, asymptotically. And then when you see GZ, attaining asymptotically decaying over time to 0, and this thing is going to disappear, and then technology at some point becomes constant. That's the math for the structure. And the reason why they put that is because when you look at the data, you see this decline in GDP growth over time. Maybe I should do this, but for some reason can't resist. Take a look at the data. So this is slide 38. We're going to discuss this. But the basic idea is that this is the data they're using over time to estimate their model. And there's various trends in the data, right, in the past. And if you look at this is GDP growth, and it's not very visible because this is the COVID recession, right? Because of the COVID, excess volatility. But the orange line is the trend, and there is a decline in that trend. Now it's not like going to 0 in the sample, but what they do is, okay, let me extend this decline that happened in the last 30 years in the data, and extending that into the future, and at some point it's going to hit 0. That's the basic bottom line. This is where this assumption comes from, that growth has been declining slightly, right? You see that orange, is this visible? This orange line is not parallel to the 0 line, it's a little tilted, right? And so that's where this assumption comes from. Okay. So they do that, and then they do yet another thing. Also on the firm side, they introduce this discounting. Again, the idea is that, right, in this economy there is now this population has a trend, productivity has a trend, and that in itself, if households and firms know about this population trend and this productivity trend for the next 75 years, they're going to be hypersensitive to that. The consumption today is going to be involving, you know, the consumption expected to change in 50 years from now, which of course makes no sense. When I think about whether I should buy a bottle of water today, I'm not going to consider myself when I'm going to be 90 years old and what you know, the world's going to look like when I'm going to be 90 years old. That's not going to happen, right? So, and that's exactly the type of thing that they're trying to do. They want to try to say, okay, my consumption today depends on what I expect my income to be today and tomorrow and the day after tomorrow. But you know, very far in the future events get a relatively low weight on my current consumption decisions. Okay? That is what this income risk stuff delivers. And then I would do the same for the firm manager. The firm manager has the same problem, right? The firm manager runs a firm and tries to maximize profit, and that firm manager knows productivity is going to go down the drain. Yeah, productivity is going to decline, and the firm manager, when posting sticky prices, is going to take that effect into account. So the firm manager, you know, will, you know, think, oh, in 40 years something bad is happening, and because of sticky prices and, you know, rolling time backward to today, what's going to happen in 40 years is going to have a big impact on today's pricing decision. Makes no sense, economic, of course. And so that's why they are putting in one additional feature that's going to break that very tight relationship between far in the future events and today's decision. And the idea here is that every firm faces a probability that it may exit. Every firm has an exit probability. So there's a chance that a firm goes bankrupt. No, they don't model this as a bankruptcy. It's just going to be an exit. This exogenously, the firm is going to close down with some probability. So some firms in this economy are going to grow very old. They're going to be very old firms, like in terms of time. But some firms are going to be more younger firms. So there's a whole distribution of age by firm. What that breaks, that you know, when you consider it, now the manager is going to do the following. It's going to consider changing the price today, but now it takes into account that, well, I may exit this economy next period, or I'm going to exit the economy possibly in 2 periods, or in 3 periods, or in 4 periods. All those possibilities will be taken into account by the firm manager when he or she decides about the price. So let's go back here to our standard model where we set up this Phillips curve, right? So this was our slide deck when we derived the Phillips curve. So now what, you know, this is the standard present value discounted profits. You're going to have one extra parameter that, you know, parameterizes the probability that you're going to exit at every point in time. And that's going to affect your Phillips curve after that. It's going to affect your future, you know, your price setting. And so it's going to get another parameter into the Phillips curve. That's what's going to happen. Finally, they are setting up a central bank that's going to choose an interest rate according to a Taylor-type feedback rule, and then they're going to do one extra thing. They're going to set up also an exogenous inflation target. And it's the same as with the population. They have better notation now. And it's the same with the population. So they say the central bank follows an inflation target. So this is not the rate of inflation that's in the economy. This is the target rate of inflation that the central bank targets. It's like, you know, the ECB targeting 2%. But importantly, they have this, you know, geometric behavior of it, in the sense that, you know, over time you can draw another time plot. What they want is the following. They want a time path of inflation. So if you plot pi t star to look like this, so it's going to attain a lower bound value. That's going to look like this. So in other words, they are trying to think about that the inflation target may have been high, but it's going to come down over time slowly to some eventual level of inflation. So this pi star infinity is just some level of inflation that the central bank is going to target. So this is pi star infinity. And intuitively, think about this as being like 2%. So the intuition is that the inflation target, pi star, if the initial rate of inflation is high, right, over time, the inflation target will come down to inflation being roughly 2%. That's it. So there is this, and the speed parameter again by which this is happening, right? Whether this is a slow rate of decay or a fast rate of decay is guided by this parameter rho. So rho is between 0 and 1. And say, suppose whatever inflation target we have yesterday, if rho is 1, or is close to 1, then it's going to take incredibly long until this is going to asymptote. But if rho is close to unity, right? If rho is close to 0, if rho is close to 0, then whatever our inflation target today is essentially going to be that there. So for low rhos, you may go very quickly down. That's the. Again, where does this assumption come from? Why are they going to take that assumption? Well, let me look at the data again. They are looking at so this is data we're going to discuss, but in the last 35 years, we've seen that there is a trend in inflation rate in the data. The realized inflation rate was this is quarterly data, so you have to multiply by 4 to get annual inflation. So this is like 8% annual inflation, and it's coming down to about 2% on average. There's this trend in inflation, and the way they interpret this trend is that central banks around the globe have, over time, thought that they want to have lower inflation rates on average. That's and they model that with an inflation target that the central bank pursues to get to that. All right, that's the environment. It works. Any questions on this?
Sorry, so because in here we have two types of household, right? So the one actually do the consumption thing into temporal is the high type, is it?
I have to be careful. There's two types of household members. So
that's because you switch on each period.
So so think about us, we are a family. And within our family, there are family members that are employed, and there are family members that are unemployed. That is the setup here. So there is a household, and in that household, there are members of the household members, family members. Let's use the correct words. There is a household comprised of many household members. There is a household members that are employed and household members who are unemployed. When we leave the door in the morning, everybody tries to find work implicitly. You guys, you found work and you work during the day. You guys didn't find work, you go to the unemployment agency of the government and collect unemployment benefits. At the evening, everybody comes home, and you guys, having labor income, you put your salary onto the table here. You guys coming home, through this door, you put the unemployment benefits onto this table. And then the family mother takes all that money and buys dinner for everyone in the family. That's the idea. So there is consumption insurance at the family or household level. Even though the household has different types of members, employed and unemployed, the family mother, or the family father decides, provides insurance. So in other words, everyone gets to get the same consumption in the evening. That's one way to think about this. And that provision of consumption insurance is so to say, one way to have that kind of thought. And so that link is going to be broken. And we're going to see this in this environment that that arrangement is going to lead to and the intertemporal decision is then done by the family model. So how much do you have consumption today versus tomorrow? Does this help? We're going to look at the equations for that meeting, and maybe this will become much clearer when we're going to look at the actual equations. Okay? And then maybe I should refine some of the things I just said. I realize, but let's wait until we get there. I think it will be easier. Okay. So there is a, yeah, let's do that now. Okay, so what do we do here then? This is the model when you're stripping out everything in terms of complications. You take out the climate, you take out the trends, you take out everything, you take out the discounting, you take out everything. That's the backbone version of the model. Okay, so that's what this slide is. And in a sense, it just shows this is almost identical to the New Keynesian model that we've been studying in the last 2 days. And then in the subsequent slides, we're going to add elements to it. Okay, so we're going to add understanding what the shocks are, and then we're going to add the discounting, right? How does this Euler and this Phillips curve discounting come in? And then we're going to add climate, right? We're going to add stuff step by step. All right. So let's start with the canonical 3-equation model. There is an IS curve, there is a Phillips curve, and there's a Taylor rule, and that's what these 3 equations are. And then effectively, these are not 3 equations, but these are 5 equations. Like here's an X-ray equation for marginal cost, but of course you could take that and plug that in for marginal cost, right? It's just visually easier to see, right? And likewise, there is an variable X that we will explain in a second that you can plug in there, and then it's going to be zero. So we have these 3 equations, and these 3 equations are like the backbone version of the model. And in terms of structure, they are getting close to what we have in our model. So let's go then in steps. What are these objects? This one, YT tilde. What is YT tilde? Okay, so YT tilde is the trended GDP. So YT tilde is output divided by ZT times LT. That's what the YT tilde is. It's the trended output. Now, what is XT? XT is the consumption to output ratio. So XT is CT tilde divided by YT tilde. So that is XT, definition of XT. Well, then you see if you take Y tilde times XT, so what is YT tilde times XT, what's that? Well, it's just going to be CT tilde, right? You want to take the definition of Y, you take YT tilde, you multiply this by XT, and you're going to see this is going to drop out against this, what's going to be left over is CT tilde. So in other words, this expression is nothing else than just consumption. This is consumption. So write this down. So this one is just going to be CT tilde. It's going to be consumption on the left-hand side. And then likewise, it's going to be consumption in period T plus 1. This one is going to be CT plus 1. It's going to be tilde. So this is the trended consumption in period T plus 1. That starts to look like a Phillips, like a Standard-Euler equation. If you compare that to our previous slide decks, right? Especially if you said sigma c equal to 1, right? If you said sigma c equal to 1, then what you're going to get is you're going to get 1 over CT tilde is equal to beta 1 over CT plus 1 tilde. That's very similar to the Euler equation that we have studied so far. R is the normal interest rate. We had the capital R. It's just different notation. And pi t plus 1 is the gross rate of inflation. In other words, it's again the real rate of return. Exactly the same structure as what we discussed in the previous paper. So it's just a different way of writing it. But at the back part of it is exactly the same. Now there's one difference here, which is this one, this little epsilon b. And that's something that we are going to discuss on the next slide. Okay? So I'm going to come back to what that shock means. So for now, I'm not going to discuss this. It's a shock. Where that shock comes from, how it shows up there, please be a little more patient. We'll talk about that. But this equation is a really standard equation. Any questions?
So can I
Yeah.
ask
Oh, sure.
something quick? So from the traditional Euler equation, right?
Yeah.
We don't have that term, but can I say that, in that scenario, that we assume that because the population growth rate is constant, right?
So what? Sorry.
For the normal model,
Yeah.
are we assuming that the population growth rate is constant?
That's right. Population
So
growth.
actually, there's a one over there, is it?
The one. This one, right?
No, because like the Euler equation is like you're comparing
Yeah.
between the marginal utility of consumption in today towards tomorrow.
That's right.
Time that another
Oh, I
ratio
see
of
what
the
you're
basis
saying.
rate, right?
That's
So
right.
in that traditional model, are we assuming that actually it's time one? But because here the population growth at the rate,
That's right.
so we need like another term to kind of like cancel out.
That's right. Absolutely. So the reason why they go with this twiddle business is precisely because ZT is growing over time and LT is growing over time, right? And so they rewrite. Remember, there's no climate change here, right? There is no climate change. There is no discount. It's the standard model. So this is what Solow told us, right? This is the Solow transformation. You're transforming your level of output that's growing over time because you have two engines of growth. You have productivity growth over time, and you have population growth over time. But you can prove that the ratio of output times C times L, that ratio is going to be stationary, right, over long periods of time. And that's the reason why they have these twiddles. And to map this back in the standard model, right, if you assume the population to be constant, you're right, then that thing drops out as equal to mu. Absolutely. So that's the end. So you could go back, and you could substitute for CT tilde, right? Let me write down CT tilde. I thought we wrote down CT tilde somewhere. Right? So if you could substitute back CT tilde, then you will find it's the rate of growth of population and the rate of growth of technology and the rate of growth of the level of consumption. Does this answer the question? Yeah? Okay. So it's because of growth that they do these transformations like you did in the Solow growth model. To have this, expressed this way. Very good. So then what's this equation here? Well, this is the resource constraint. This is the economy resource constraint. It doesn't look like it, but it is. So this is the resource constraint. And so why is that? Well, you can just write this economy. Let's rewrite this, the resource constraint a little bit. So this is, in this economy, there's no physical capital, there's no trade. So on the use side, every piece produced is used for consumption expenditures. Right? There is no investment. Typically what we have in the national income per accounting, that GDP is equal to C plus I plus G plus net exports. There is no investment, so there's no I, there's no government spending, no G, and no trade, no X minus C. So the left-hand side is all the resources produced in this economy are used eventually for consumption purposes. And that equals all the output produced minus a term which accrues to the Rotenberg pricing adjustment costs. Right? These are costs, these are resource costs. When firms change their prices, this is costly. It's a resource cost. So you have to subtract this term kappa pi t minus pi star t squared, which are the Rotenberg costs. So this is the Rotenberg cost by t tilde. So this is Rotenberg. Okay. So the resource constraint is everything is produced net of the Rotenberg adjustment cost, which is the Rotenberg cost per unit times the amount of output produced. So that's the resource constraint. Now you are dividing this by y tilde. Divide this entire equation by y tilde, and as a result you're going to get ct tilde divided by yt tilde is equal to 1 minus kappa, and I'm just going to deviate the parentheses. So you divide this by y tilde, and the y tilde disappears here, this becomes a 1, and then this becomes c over y. It's exactly this equation. So in other words, this is the resource constraint that we are living in this economy. You could, yeah. Any questions? Now, when you're log linearizing the model, this thing is going to disappear. We never saw that in the other slides, right? The resource costs, and because when you log linearize, because this in steady state is 0. When you log linearize, this disappears. But here we want to work with the nonlinear model, so that's why we have to keep this around. Okay, good. If there are no questions on this, then let's proceed to the next equation. And this is the New Keynesian-Phillips curve. So this is the PC, stands for New Keynesian-Phillips curve. And in terms of structure, folks, we have seen this in our other slide deck. In particular, you know what this zeta parameter is? It's the omega that we had in our other slide deck. So the zeta here, is equivalent to the omega price adjustment cost in the other slide deck. And then if you take a cup of tea or coffee and you just hold both slide decks next to each other, you will see the same structure, right? So let's go here to our New Keynesian model slide deck where we developed this Phillips curve, and you will compare this equation number 3 with the Phillips curve in Fernandel, Smets, and Sabu, and you will see very similar components. You will see there is a constant term, there is a marginal cost term, there is an inflation quadratic term, and then there is a future expected term. It's exactly the same structure to what we've been studying so far, right? So there is a constant term, right? So this is the theta term that's constant in the other slide deck. Then there is a marginal cost term. Then there is this t plus 1 term, and then they just wrote this in the other side of the direction. This is the inflation square term. It's exactly the same structure. Is that beautiful? I don't know. Every time I look at that, I say, I know where that equation comes from. No? So it's really neat to have that mapping that when you look at that equation now, you know where this equation comes from, how it's being derived, and what's in the background there. Now there's one extra element, there's this growth term there because productivity grows over time. Right? So there's small but really subtle differences. Nothing that's major and new and Then we have a marginal cost term, which essentially in this, you can plug that in there, and then here marginal costs are a function of consumption and output. Now, under specific parameterizations, this marginal cost term is going to be exactly the same as the one that we have used so far. Okay? So it depends a little bit on these extra parameters, sigma c and sigma n. What the values of those are, but conditional on those, you will see this is going to be exactly the same. There is a term that I want to highlight, that we will be discussing on the next slide deck, on the next slide. So let me maybe annotate this. I want to just make this is a green dot here, and also let me put the green dot there, just to remember that we're going to talk about that on the next slide. I'm not talking about that term. And then finally, we have a Taylor rule that, except for one feature, looks very similar to the Taylor rule that we had. The interest rate, the nominal interest rate, let's write this down explicitly. So this is the nominal interest rate. Right, so this is the policy rate, the nominal interest rate, or the policy rate. So the interest rate that the central bank decides upon is a function of stuff. Let's go from inside. So what is this? This is what we call the output gap in the other paper. This is the output gap in the other paper. I cannot write xt because xt has a different meaning in this version. But this is the output gap. So let me write this down. That is the output gap. Right? We call that xt in the other table. Then we have another term in here. This is what we call high t hat in the other paper. So this is inflation and deviation from the target. The target in the other slides was constant. So we only had inflation, right? And in the other slide deck we only had inflation there. But now it's inflation and deviation from the target. So if inflation is like 10% and the target is 2%, then the central bank will react with its policy rate to that inflation gap. Right? If inflation exceeds the target, it will raise the policy rate, and vice versa. So that's the inflation gap. Okay? It's the so-called inflation gap. And then what this term is not you can interpret this a little bit as the inflation target. So when the inflation target is high, your nominal interest rate is going to be high. That's another way of thinking about this, right? So suppose you are living in Turkey or you're living in Zimbabwe or Venezuela a couple of decades ago, when inflation was like 50% or 100%, nominal interest rates are very high. And so that Taylor rule takes that up in detail. Okay? Depending on, after all, if the inflation gap is closed, if the output gap is closed, okay, those two things are all closed, then this rule must, of course, yield that it obeys the Fisher equation, that the nominal interest rate is the product of the real interest rate times expected inflation. That's what this is. It's a standard term.
What is the pi value index?
I think that's a great question. I don't have an answer to that right now. It looks like a typo. Rui, can I come back to you with on that one tomorrow?
Yes.
It looks like a typo, but I'm not sure. I need to figure this out. Sorry, but that's something that's good to know. We use a different color, and by tomorrow I will give an answer to that. We could read the paper right now, but I want to use the last 2 minutes to wrap this up and make sense of what else is in this equation. Now, then there is this term in here. So what does this say? The interest rate by the central bank said today is a function not only of all that stuff, but also the lagged interest rate. It's the lagged interest rate. So the interest rate yesterday. And so rho is a parameter between 0 and 1. Rho is a parameter between 0 and 1. And it captures the degree of so-called interest rate smoothing. Central banks, if possible, like to go slowly with their policy rate. They always go in steps. Remember when they do press conferences? Oh, we have increased by 25 basis points. Or we have increased by another 25 basis points. Right? So the central bank often uses interest rates going in small steps. And so there's, they do that for a variety of reasons. The big reason is they want to smooth the interest rate. They don't want to, make financial markets nervous by overly excessive swings in the nominal rates. In other words, they don't go to 10% today and 6% tomorrow and 8% tomorrow. They don't want that, but they want, provide, small steps. And that's basically what this is. This means that the interest rate today is a function of yesterday, and if this rho gets to 1, then it's going to be very slow that the interest rate is going to change. So in other words, that's called interest rate smoothing. And the idea is to have slowly evolving policy rates as we see it in the data. Finally, there is this pi t star, which is, they have extended this rule so that the deviation, the rate of change of the inflation target also matters. It's a little weird. I don't have good intuition for it. But it's like the rate of change of the inflation target affecting also the nominal policy rate. In the end, they're estimating these parameters. So the rho is going to be an estimated parameter. The phi pi, the phi y, and the phi pi star, they're all going to be estimated parameters. So the data will tell us how important that term is. That's one way to think about this. So there's you can always, in applied work, when you estimate models, you can always think about, let me extend this maybe by an additional term, like for instance the policy rule, and then the data could tell us, oh, that must be 0, or no, that's actually non-zero. And then, that's one way to think about this. Okay, now let me then wrap up this slide deck, this slide number 12, and there is one more shock. Let me also put green on this one, and that's green, right? That's the Monteponti shock. Now I'm going to ask you 4 questions in 1 second, but I just want to move forward and tell you what these shocks are in words. Okay? The shocks that we have in this model. what they are in words, and then tomorrow I'm going to take a little more time to explain in detail. This is a one-tripolsic shock, just as what we did. So we called this upsilon t in the other slide deck. So this was the upsilon t we used in the other slide deck. This is what they call a supply shock. This is the AT shock. This is the cost push shock in the other slide deck. So this is AT in the other slide deck, so the cost push shock. That's what they have here. Okay, so it's the same. Yeah, that's the reason why I tossed in that extra slide deck on the cost push shock. It's exactly the type of thing. So they want this because of the correlation they want to explain. They want to estimate the model. When you want to estimate the model, you may have to make sure that the model can get that shotgun blast that we see in the data. That's the reason why that happens. This shock we haven't seen yet, and I'll explain that tomorrow, where that shock comes from, but it's very simple. It's very simple in the sense of it's a shock to the utility function. It's a preference shock. It's a marginal utility of consumption shock. It's like you're waking up tomorrow morning or tonight. You are, after studying hard, you're getting up from your desk. You say, now it's time to go on shopping, friends. I want to shop, whatever food and you are like overly happy about doing that. But we'll talk more about that tomorrow. All right. Let's get back to this one here. Are there any questions? Any questions so far on the material that we covered here on this microclimate model part? You all have read the paper, right? I mean, that was the Monday afternoon task. Are there any big questions you have when you read the paper that we haven't been addressed so far? I mean, I'm asking, like, with the stuff we covered, is there any gap between what you read and maybe wrote down in terms of questions relative to what we've covered so far? Is there any big gaping question mark? How is the speed by which we are going through this? Is this appropriate? Too fast? Too slow?
Speed.
Speed is okay?
Because for me, at first I read the paper, I don't know why there are a lot of equations that we did not see before.
Yeah.
And why they use it for this case, and should could it apply for another case, for another data, for example, for another country problem, for example. So I just following the 12 slide, and I popped the idea that we must focus on the question and the problem linking first. For example, at first for the ingredients, slide number 10. So I saw that they have the new equation on the population size exogenous, and the other is for exogenous technological trend. So that is very, very different from the theory we have learned before. And I saw that is a pop-up idea, because the population is one of the key idea which make the climate effect is bigger. And the other side is the technology is also important for decrease in the impact
Because of climate.
Yeah.
That's exactly right.
Yeah, that's why I think that when we pop an idea in the research, so we need to collect the relation at the beginning, and then of course we referring on the other literature to get the correct equation to mention the problem and link it to the equation here. So yeah, I follow that till now, because at first I read the paper, I don't know why there is many strangers, many
Yeah,
So now I get the idea.
You get the idea.
Yeah.
Okay. So
How
if you
to
like,
do it.
right, you're right, the paper is full of equations, right? And it's a little, you can get lost in all these equations, but these equations are necessary. Once you do all the derivations, you're going to get to this, right? But of course, your deeper question is, why do they have, population growth? Why do they have technology, all that in? It's all going to come together with the features that we are going to discuss when augmenting this model, right? But I agree that the math can be a little overwhelming.
Yeah.
I want you to understand that the math is just a tool to get to these equations.
Yeah.
With enough effort and enough coffee and tea, you will be able to derive these equations eventually. That's not required. That's not the task of this course. Right?
Yeah, I know.
I don't require you to be able to do the derivations of, say, this very equation, or this very equation. You must understand where these equations come from. You must understand what are the implications of those equations. That's like what you're saying.
Yeah.
And I hope that tomorrow, when we go over this over and over, and it becomes more intuitive and better to understand.
Yeah.
Perfect. Okay, so I'm going to owe you an explanation for what that pi is, and then we'll see each other tomorrow. Thank you very much, and have a great rest of the day, and I'll see you tomorrow at 9:15.
Yeah.
Thank you.